Hello everyone and welcome to lecture 17. This is the last section that we're going to talk about in chapter 3, and I wanted to just spend a little time on looking at the graphs of polynomial functions. Last time we talked about polynomial functions in general, so now we're going to look a little more carefully about the graphs. So the first thing that's important is that graphs of polynomial functions are smooth, right? They have smooth curves. There's no breaks. There's no sharp bends or kinks in the graph. So I drew 4 graphs here, and we want to determine which ones are polynomials and which ones are not polynomials. So if you look at this the first graph, here I have nice smooth turns. Actually, what's the smallest degree that this polynomial could be? Well, there's 1, 2, 3 turns, right? So this is probably a 4th degree polynomial, but it's definitely a polynomial because I have a nice smooth curve there. So this is definitely a polynomial. Okay, what about the second one, the one to the right of that? Well, same thing, right? Smooth turns. In fact, in this case, I have 2 turns, right? Smooth curves. There's no kinks. There's no jumps. So, and actually in this case, I have 3 x-intercepts as well. This looks like it's of degree 3, right? It's a cubic function. So that would be a polynomial of degree 3. But for our purposes here, we just want to know whether it's a polynomial or not. Yes, it's definitely a polynomial. Okay, what about this blue graph here? Well, this is definitely not, right? Because it has a sharp point, like a kink there where it switches. Actually, this is an absolute value function, right? So it's not a polynomial. And in here, the last graph, if this were to keep going, right? If it didn't have it jump here and it just kept going, that could be a polynomial. But it's kind of like a piece of a polynomial and it stops and it jumps. So as a whole, this is definitely not a polynomial. Right, there's a break in the graph there. So because there's this break, it can't be a single polynomial. Okay, we talked a little bit about local behavior in the last lecture. Let me mention a little bit more about that. So in particular, we can use factoring, right, to find the zeros of a polynomial function. Let me just do an example on that. So I'll say using factoring. To find zeros of polynomial functions. Either I'm going to give you the polynomial function in factored form, which will make it easy to find zeros, or it's going to be something that's easily factorable. So since we didn't talk too much about ones that are easily factorable, let me just mention that. Okay, so let's say I'm given this. I'm given p of x is equal to x cubed plus 5x squared minus 14x. And I want to find, I'll call it a p-intercept and the x-intercept. All right, so let's do the p-intercept first. So the p-intercept, remember, to find that, you set x equal to 0 and you solve for p. Or in this case, since I have it as a function, I can just evaluate the polynomial function at 0. And if you do that, what are you going to get? Well, in this case, right, I'm going to have 0 cubed plus 5 times 0 squared. This should be a 0. minus 14 times 0. Well, that's just 0, right? So the p-intercept is just going to be the origin. It'll be the point 0, 0. Okay, what about the x-intercepts? Well, to find them, I now set the entire function equal to 0, right? Set p equal to 0 and solve for x. And normally that would be it could be quite difficult to do, right, for a cubic function. But if you look at this, this is easily factorable, right? So I'm going to set the entire function equal to 0, okay? Now let's factor this. Well, first thing you should notice is that an x is common to every term, so we can pull out that x, and we're left with x squared plus 5x minus 14. And now let's see if I can factor this trinomial term here. Well, the only way I can get x squared is if I multiply x times x. And this is factorable if I can think of two things of multiplied give me negative 14 and added give me positive 5. So can you think of two things of multiplied give you negative 14 and added give you positive 5? Yeah, if I do, I guess, positive 7 and a negative 2, right? If I multiply them, I get negative 14. If I add them together, I get positive 5. Okay, so equals 0. So now it's in factored form. So I can set each factor equal to 0. So one possibility is x equal to 0. Another possibility is x plus 7 is equal to 0. Another possibility is x minus 2 is equal to 0. So if I solve these, right, one is just x equals 0. The other possibility is x equals negative 7. And the last possibility is x is equal to 2. So actually, these are my zeros, right, or roots. Those are the x values. X equals 0, x equals negative 7, x equals 2. If I really want the x-intercepts, then I have to write all of these as points. So one of them is, again, just the origin, right? In fact, in this case, it's both an x-intercept and a y-intercept. Then I have negative 7 comma 0. That would be another x-intercept. And finally, 2 comma 0. Okay, let's look at a more complicated polynomial function. Okay, so now what we want to do is we want to look at identifying zeros in something called their multiplicities. So identifying zeros and their multiplicities. And to do that, I want to look at one particular polynomial function. So let's examine the graph of this polynomial function. F of x equals 1/12, so that's just a constant out front. And then these are the important factors. X, I'll write it in factored form. X plus 3 times x minus 2 squared times x plus 1 cubed. Okay, so this is the graph of that function, right? Now, in general, if you were asked to find the x-intercepts or the zeros, how would you do that? You would set that function equal to 0 and solve for x, right? So here, let me do it down here. Let's so find the x-intercepts, or I'm also finding the zeros, right, when I do that. So I'm going to set that entire function equal to 0. So the first thing I could do is I could multiply both sides by 12, right? So the 1/12 doesn't even matter. Really, you could write this as x plus 3 times x minus 2 squared times x plus 1 cubed equals 0. You multiply both sides by 12 and it gets rid of the 1/12. Then notice, in order for this to be true, one possibility is that x plus 3 could equal 0. Another possibility is x minus 2 squared could equal 0. Another possibility is x plus 1 cubed is equal to 0. Well, the first one is going to give us the 0 x equals negative 3, right? Or the root x equals negative 3. Or if you want to write it in terms of an x-intercept, this would be negative 3 comma 0. The second one, if you're being careful here, right? Remember, this means x minus 2 times x minus 2 equals 0. So both of these are going to give you the solution x equals 2. Because it appears twice, right? Because of this exponent here, what we say is this has multiplicity two. Or some people will say it's a double root. Right? And really it's a square that tells you that, right? Because that means x minus 2 times x minus 2 equals 0. So we're getting the same solution, x equals 2, but twice. Okay, and again, the actual x-intercept would be 2 comma 0. And then the last one, right, this is really like x plus 1 times x plus 1 times x plus 1 equals 0. So if I solve that, I'm going to get x equals negative 1, x equals negative 1, x equals negative 1. We get it 3 times. So this x equals negative 1, we say it has multiplicity three. So it's called a triple root. And its x-intercept would be negative 1 comma 0. And by the way, the one that I did at first, because this, if you want, you can think of this raised to the 1 power. This is really just multiplicity 1. Multiplicity 1, right? It's a single root. Okay, so it's really the exponent that determines the multiplicity, right? Do you really have a single root, a double root, or a triple root? And we won't get anything more complex in this class than triple roots. So let's see what this looks like graphically, right? So if we look at this graph, so this is a graph of that function. Notice here, right, that this root, x equals negative 3, remember that came from this factor, right? That came from the x plus 3 factor. So I'll say the x equals negative 3 root comes from the x plus 3 factor. Because remember, when we set the equal to 0, we get x equals negative 3. And we know that since it's to the 1 power, right, this is really 1 power, it's a single 0 or single root. I'll call it 0, single root. That means the multiplicity is a 1. And notice what it looks like graphically. It looks like a line, right? A line passing. If you get really close to that point, it looks like a line. The graph looks like a line that passes through negative 3. Okay, let's look at, I'll do this in a different color, this root right here. So x equals negative 1. Well, that, right, that root comes from this factor, right? So the x equals negative 1 root comes from the x plus 1 cubed factor. And it's a triple, we know that it's a triple 0. or triple root, and the multiplicity is 3. Right? Triple means multiplicity is 3. And what does it look like? What does the graph look like close to that root, close to that point? It looks like a cubic function, right? So it looks like a cubic function. Okay, and then we have another root here. Right, so in this case, this x equals 2 root. It comes from setting the x minus 2 squared factor equal to 0. Right, so it comes from the x minus 2 squared factor. Right, so it comes from this factor. So this is basically a double root or you could say it has multiplicity 2. Right? So double root has multiplicity 2. And what does it look like if you look close to that root? So what does the graph look like close to that root? It looks like a parabola, right? It looks like a quadratic function close to the root. So the graph looks like a parabola, right? Or a quadratic function. And that will always, so it kind of just touches, right? It touches the x-axis and bounces off. And that will always be the case. It could come from below and touch it, or it could come, in this case, from above and touch it. So a single root, right, in this case coming from the x plus 3 factor, graphically it's going to look like a line that passes through. A double root, so coming from the x minus 2 squared factor, it's going to look like a parabola or a quadratic, just touches and bounces off. Right, so near that root, it looks like a parabola. And then a triple root looks like a cubic function. So near that function looks cubic. Right, and again, we won't do anything higher than that. It turns out like if it had multiplicity 4, it would look like a parabola that's flatter. Right, it would look like next to the fourth function. If it was a higher odd exponent, it would kind of look like a cubic function but flatter. Right, but we're only going to deal with, at most, having an exponent of a 3. Okay, so let me give this rule in general. So in general, with the factor so if you have some polynomial and you have a factor x minus, I'll just call it h, right, some constant, to the p power. If p is equal to 1, so something like this, let's say at that root, right, it's a single root. This would be an example of p equals 1. So it would be a single root. And what does it look like near that root? The graph looks like a line. It looks like a line. Okay. What if p is 2? So what if that exponent is a 2? Well, then the graph, if you look close to the root, the graph's going to touch it and go off. Or it could do this, right? Again, it could be like either case, like either here or here. So in this case, we have a double root. And it looks like near that root, the graph looks like a parabola. So say it looks like a parabola. Okay, actually let me erase this. I don't want to confuse you and put two. So it could either look like that, or this would be the same thing. So this would be a double root there, and it's going to look like a parabola. And then the other case is let's say I have p equals 3. So let's say at that 0 right there, p is equal to 3. So this is also p is equal to 2. Then I have a triple root. And what's always going to be true, it'll look like a cubic function. So it looks like a cubic function. And again, depending on the polynomial, it could be flipped, right? So this would also be a case where p is 3. What if it does this, like that? Then that would also be p is equal to 3, right? It looks like a cubic function near, so that'd be a triple root, looks like a cubic function right near the root there. Okay, so here, let's do some examples of this. Let me give you a picture of a polynomial, and we want to write the equation. We want to find the equation for it. Okay, so let's say we want to write an equation for this polynomial. Okay, so what's going on here? Well, it looks like we have how many zeros or roots do we have? It looks like we have 3, right? So we have a root or a 0 right here at x equals -4. Now, based on the shape, right, of the graph near that root, is that a single root, a double root, or a triple root? In other words, is its multiplicity a 1, a 2, or a 3? Well, because it looks like, right, it looks like a parabola near that root, then we know that the multiplicity is 2, right? It's a double root. So it's a double root. Here, I have another root at x equals 1, and I have another root at x equals 2. In both cases, right, if you were to zoom in, so if we zoom in here at 1, it looks like a line, right? And same thing at x equals 2. It looks like a line. The more we zoom in, the more it looks like a line. So in both of those cases, the multiplicity is 1, right? They're just single roots. So these are single roots. What else do we know? Well, actually, there's one other point that we can easily locate here. I can locate the y-intercept, right? Where does the graph pass through the y-axis? It's this point right here. So this is 0, -2. This is our y-intercept. We might need that later. All right, so to summarize, right, I have, I'll make a little table here. I have my roots, which are also called zeros, and their multiplicities. So I have x equals -4, x equals 1, x equals 2. And remember, the multiplicity was 2, 1, 1. Okay. So I know that my polynomial has to have this following form. First of all, there could be a constant. We don't know what that is. We can figure it out. I'll show you how to do that later. But for now, let's just call it like a. Just some constant out front, right? Now, the root x equals -4, what factor does that come from? Well, the factor must have been x plus 4, right? Because if I set that equal to 0, I'm going to get the solution x equals -4. So the factor is going to be x, and then it's the opposite sign, right? X plus 4. And because the multiplicity is 2, this factor must have been squared. So I know that one factor here has to be x plus 4 squared. What about the x equals 1 root? Well, it must have come from the factor x minus 1, right? Because if I set that equal to 0, then I'm going to get the solution of 0, x equals positive 1. So the factor must have been x minus 1, right? You have to change the sign on the factor. And since it's multiplicity 1, I don't have to do anything, right? There's already, I'll write it in here, but normally you don't write the 1 there, right? There's already a 1 there. So this is just going to be x minus 1. And then finally, the x equals 2 root, or 0, also has multiplicity 1. It must have come from the factor x minus 2. So I know I have another x minus 2 here. Well, if you look at that, I'm almost done, right? All I need to do is figure out a. If I can figure out the coefficient a, that, the value of a, then I have the equation for the polynomial. So how do I figure out a? Well, I need some other point to plug in. I can't use the roots to plug in because that's just going to give me 0. It's not going to help me. But notice here that I know another point. I know this y-intercept is 0, -2. So I'm going to use that to figure out a. So I'm going to say use the y-intercept, the point 0, -2, to find a. So I just plug it in, right? Where I have a p, my output, that's going to be -2. I guess if we're being careful, right, this is, you can think of it as the p-intercept in this case, because I called it p instead of y. But same thing, the output is a -2. That's got to equal a, and then the input is going to be 0. So wherever I have an x, I'm sticking in a 0 now. Okay, so I have -2 equals, well, this is what a times 4 squared is going to be 16 times -1 times -2. So this is -2 equals, well, 16 times -1 times -2 is positive 32. So this is 32a. And if I divide by 32, and you can simplify that, we're going to get a is equal to -1/16. So now I have my answer, right? My polynomial of that graph that we saw above must be -1/16, that's a, times x plus 4 squared times x minus 1 times x minus 2. So that's going to be the equation of that polynomial. Oops, I want a square there. So x plus 4 squared times x minus 1 times x minus 2. And that coefficient out front was -1/16. Okay, so that's one way, right? We can find the equation is given a graph. Let's do some other different examples. Let's try this. So I want to find a formula, so an equation or formula for the polynomial I'll call it p of x, with these things. It has to have degree 9. So it's got to be a 9th degree polynomial. It has to have a leading coefficient of 1. Well, that basically tells us that a is equal to 1, right? A root of multiplicity 2 at x equals 0, a root of multiplicity 2 at x equals 7, and a root of multiplicity 5 at x equals 10. So can I find a polynomial that fits all those criteria? Okay. Well, first of all, if my 0, right, let's look at this one first. If my 0 is x equals 0, and it's a root of multiplicity 2, that means the factor must have been x minus 0, and then multiplicity 2 means it was squared, right? But we never write x minus 0. We would just write this as x squared. That must be one of the factors, okay? Now, if I have another 0 or another root at x equals 7, then the factor must have been x minus 7, right? That led to that. And since it's multiplicity 2, this is squared. And then finally, if I have a root or a 0 at x equals 10, then the factor must have been x minus 10 that led to it. And since it's multiplicity 5, then the exponent has to be a 5. So if we put this all together, right, then we know that the polynomial will have this formula. So the a is a 1, right? We've been told that the leading coefficient is a 1, so a is 1. Then it has this x squared term, right? That accounts for the first part where the root is 0 and the multiplicity is 2. Then I have an x minus 7 squared term. That gives me the root x equals 7, right, with multiplicity 2. And then I have this factor x minus 10 to the 5th. That was the x equals 10, 0, or root in the multiplicity of 5. So that's it. That's my equation. This would be the equation of that polynomial. Okay, here's another example. Let's say you're told the polynomial of degree 3 we will again name it p of x, has a root of multiplicity 2 at x equals 5, and a root of multiplicity 1 at x equals -4. You're also told the y-intercept is 0, -20. We're going to need that because we need a point. We're going to need a point to figure out the leading coefficient, right? The a term. So now we want to find a formula for p of x. Actually, before I do this problem, let me go back to the other problem just for a second. Remember, another thing it told us, right, at the beginning, it said that the degree of this polynomial was 9. Well, let's check that. Does that make sense? Well, if you were to expand this out, do you guys see how, first of all, I have an x squared term here, right? If I expand out this second term, x minus 7 squared, that second factor, I'm going to get another x squared term, right? And if I expand out this x minus 10 to the 5th, I'm going to get like an x to the 5th plus a bunch of other stuff. So if I look at all my leading terms of each of these factors, I have x squared, I'm going to have another x squared, and I have x to the 5th. Well, if I multiply those together, right, remember you add the exponents, it'd be 2 plus 2 plus 5, which is 9. So this is going to be x to the 9th plus something, right, plus a bunch of other factors. But the leading term is going to be an x to the 9th, right? So that makes sense that this does have a degree of 9, right? It's a 9th degree polynomial. All right, I just wanted to point that out, that matches what we were given. Okay, in our problem here, we're told the polynomial has degree 3, Okay, it has a root of multiplicity 2 at x equals 5 and a root of multiplicity 1 at x equals negative 4. All right, so that tells us, I can start writing this out now. I have p of x. I could have some coefficient a, right? It doesn't necessarily have to be 1. It could be some other value, so I'm going to leave that as a for now. Now, I have a root of multiplicity 2 at x equals 5. So the factor must have been x minus 5, right? That's how I'm going to get a root of x equals 5. The factor has to be x minus 5. And since it's multiplicity 2, that's squared. And then I have a root of multiplicity 1 at x equals negative 4. So this factor has to be x minus a negative 4, but it's the same as x plus 4, right? Because if I set that equal to 0, I'm going to get the solution x equals negative 4. And multiplicity 1 means the exponent is a 1, so I don't really have to do anything else. And that's it. So the last thing I need to find is a. Once I find a, I'm done, right? I have my equation. Well, how do I find a? Well, we're given some more information. We're told another point that this polynomial passes through is the y-intercept, which has the coordinate 0, negative 20. So if my output, my p is negative 20, that means my input, the x is 0. So negative 20 equals a. Well, negative 5 squared is positive 25, and I have a 4 here. So this is negative 20 equals 100a. And then I can divide both sides by 100. So I'm going to get a is equal to negative 1/5, right? So now my polynomial, the final answer, is going to be negative 1/5 times x minus 5 squared times x plus 4. And notice, if you were to expand this out, right, this term is going to have an x squared. The leading term is going to be like x squared. This one, it's an x. So an x squared times an x is x cubed, right? So it's a third degree polynomial, as we expected. You don't even have to do anything else. You just look at the largest term. Well, if I square that, it's going to be x squared. And then x squared times x is x, right? You don't have to actually expand it out. Just look at the largest terms, and that will give you the degree of the polynomial. Okay. Oh, what about this? Okay. Let's say we're given y equals x minus 2 times x plus 3 squared times x plus 1 cubed. And I want to find the zeros and the end behavior, or the long run behavior. Okay, let me start with the zeros. All right, I'll start with the zeros, or the roots. So how do we find that? Well, we set the entire thing equal to 0, right? So I have x, we set y equal to 0, basically. So I set this entire polynomial equal to 0. Okay. So one possibility is x minus 2 is equal to 0. Well, that's going to lead to the solution x equals 2. And the multiplicity in this case is 1, right? Because there's just a 1 in the exponent there. It's a single root. Another possibility is x plus 3 squared is equal to 0. You could write it as x plus 3 times x plus 3. Since I'm really getting the answer x equals negative 3 twice, right? So if I set each of these equal to 0, I'm going to get x equals negative 3. But I'm getting that same answer twice, so this has multiplicity 2, right? It's a double root. And then finally, if I set the third factor equal to 0, this really means x plus 1 times x plus 1 times x plus 1 is equal to 0. So I'll just do one of them. If I set one of them equal to 0, I'm going to get x equals negative 1. And that is multiplicity 3, because I'm really getting that same answer 3 times, right? So multiplicity 3. Okay, now So those are the zeros, right? Or the roots. How do I find the end behavior? Well, the end behavior only depends on the leading term, right? And notice here, if we expand out, here, I'll write it down on the bottom again. So I have y is equal to x minus 2 times x plus 3 squared times x plus 1 cubed. What's the leading term from that first factor? Well, that's just an x, right? What's the leading term in the second factor? Well, if you expanded this out, if we actually went over the side and expanded this out, and you don't have to do this, you can kind of just think about this in your head. The leading term is going to be an x squared, right? Plus, and then we're going to get things smaller than that. We're going to get like a 6x plus a 9 in this case. But we're going to get something smaller than x squared. So the leading term from that factor is x squared. And then if I expand out x plus 1 cubed, what do you think that the leading term is going to be? It's going to be x cubed. So if I multiply all those together, I'm going to get x to the 6, right? Remember, you add the exponent. So 1 plus 2 plus 3 is 6. So it's x to the 6. So this polynomial looks like x to the 6th, right? Just when we're dealing with end behavior or long run behavior, we only care about the leading term. Well, we know what x to the 6th looks like because it's an even exponent, right? So it kind of looks like a parabola but flatter in between a -1 and 1, and it grows faster outside of that. So it looks something like this. But the important thing is, from knowing that, right, we can figure out the end behavior. So as x goes to infinity, that polynomial also goes towards infinity. I think I called it y in this case. I'll say y goes to infinity. And as x goes to negative infinity, y again goes to infinity, right? In both cases, the graph goes up, grows without bound, right? Because that's what x to the 6 does, and that's the only thing we have to look at when we're looking at end behavior or long run behavior. The other terms in here are not going to matter. It's just going to be that leading term, the x to the 6 term, that's going to tell us what happens when the input gets really, really large or really, really small. Okay, and then let's do one last question. Let's say you're asked to write a polynomial function with the given zeros and multiplicities. Okay, so let's say, I'll make a little table again. Let's say for the zeros, I have x equals 7, x equals -4, and x equals -3. And if for multiplicities, let's say this is multiplicity 1, 3, and 3. Okay. So let's figure out what the factors must have been, right? That in order to get those zeros with those multiplicities. So the factors must have been what? Well, if the zero is x equals 7, then the factor must have been x minus 7. And since it's multiplicity 1, that's it, just x minus 7. If the 0 is x equals -4, the factor must have been x minus a -4, but we'd write that as x plus 4. Right? Because if you solve that and set it equals 0 and solve it, we're going to get x equals -4. But this has to be cubed because the multiplicity is 3. And then finally, if the 0 is x equals -3, the factor must have been x plus 3. And then since it's multiplicity 3, it's going to be also cubed. Okay, so the sign is always the opposite, right? Because think of it, you're setting each factor equal to 0 to get the 0. So the sign is going to change on the factor. All right, so we know that, I'll write it as p of x. It has the form a, right? Then it's going to be x minus 7, x plus 4 cubed, x plus 3 cubed. And because it didn't give us any more information, in fact, usually in this question in my open math, it'll say there are many answers, then it doesn't matter what we make a. A can be any constant, right? Except 0. It wouldn't make sense to make a 0, but a can be anything else. So for convenience, maybe just like whenever you get a problem like this and we don't have to figure out a, just let a equal 1, right? Then you can say that the equation must have been just x minus 7 times x plus 4 cubed times x plus 3 cubed. And that will be the correct answer. Okay, so we don't have enough information to specify a, but my open math will take any value that you put in for a. We're just going to make it easy, make a equal to 1. All right, great. So that's it for all the material that we're going to cover in Chapter 5. And next, what we're going to do is jump into Chapter 7, which will talk a little bit about trigonometry. So like right triangle trigonometry, sine, cosine, that sort of stuff. And if we have time, which we should, we're going to talk a little bit about some applications of trigonometry. In particular, we'll talk about vectors. Great, thank you.